Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's get into lesson 6.1.3, and I'm just going to tell you right now, if I seem a little sad, I'm not giving this lesson as much energy as normal. It's because I just said some of the most wonderful things to teach you about boundary points and realized that I had not been recording. So I think I went on for like 2 minutes, but okay, I'm over it. All right, so the first term we're going to use here is, I'm going to front load this to you. It's going to come in later in the lesson, is the boundary point, okay? The boundary point of an inequality is the number on the number line that separates all solutions from numbers that are not solutions, okay? So I just want to make something that's clear to you. If I said, let me actually change this to x is greater than 5, greater than or equal to 5. I'm going to now have to shade this in, and I'll explain why in a second. All right, let's put this into the context of a real-world situation. We've sort of established that kindergarten starts for students when they are 5 years old. We don't like to have 4-year-olds in kindergarten, and you can't have 3-year-olds in kindergarten. But if you're 4 in August and you're going to turn 5 very, very quickly, like September 1st, then you could technically be 4. But for the sake of my argument, let's say that you got to be 5 years old the day that kindergarten starts, or else you can't come to public schools. Well, this inequality would sort of represent that situation, where x is any number that's greater than or equal to 5. Okay, so we're not going to list all the possible ages that you can be for in elementary school. We just state it as this: x is any age that's greater than or equal to 5. And so if we want to express that on the number line, we would find where the number 5 is on the number line, and we'd circle that number. And then everything to the right of it is a number that's greater than 5. So since x is any of these numbers that's greater than 5, then the 6, the 7, the 8, everything up to infinity would be considered a solution for this situation. And now the whole circling it, if this said x was just greater than 5, we would only circle the 5. But then everything greater than 5 would be a solution. So like 5.1 would be a solution, or 6 would be a solution, or 5.0001 would be a solution. So it's impossible for us to figure out what the lowest number would be that would be a solution because of the nature of the infinite number of decimal places that you have. So we just circle the 5, and we just accept that anything greater than 5 is going to be a solution. So you pick a number, as long as there's a 5 in the ones place and something more than 5 or more than 0 in the decimal places, and that would be on this side of the number line. But the moment we add is greater or is equal to this inequality symbol, then we're including the number 5 as a part of the solution set. So we would want that part shaded in as well. So the boundary number sometimes is left open when you've got an inequality symbol that does not include the equal sign. But the moment we include the equal sign, then the boundary circle also gets shaded in, to imply that that number that is circled, the boundary number, is in fact a solution to the problem. All right, so let's get to it. You have used expression comparison maths to compare two expressions and found that sometimes it's possible to determine which expression is greater. In this lesson, you will again compare expressions. This time, you will find the values for the variable that make one expression greater than another. All right, so I'd like for you to copy these down while I'm reading. Maria has been recording her work to see which side of the expression comparison math is greater, but she has been called away. Garth looked at her work, but he cannot figure out what Maria did to get from one step to the other. Look at Maria's work here for both mat A and for mat B, and help Garth by building the expressions on your mat and simplifying them. Okay, so remember, you can use these algebra tiles here to build what she's got there. Feel free to do that and manipulate these situations because you don't actually have the physical maths in class to build this. Write him a note explaining what Maria did to get from one step to the other. Okay, so I want you to take a little time and see if you can figure this out, and then we'll do the reveal in a moment after you unpause. Okay, so if you built this using the online tool, it would look something like this. You got your 5 x's, your 2 1s, and your 6 negatives on mat A, and you got your 2 x's, your 2 1s, and your 8 negative 1s for mat B. So what appears to be happening here to go from 2 plus -6 to -4? That's the whole idea of removing zeros, right? And to go from 2 plus -8 to -6, same thing. This step involves the removing of zeros. So removing 0 pairs was her first step right here. Then she went from 5 x's to 3 x's and 2 x's to no x's right there. So what was that step? That idea of removing the same amount of x's from each side, that's the removal of balanced sets, which I lovingly call removing the BS. Then you can do it again, right? You got a -4 and a -6, but if you take away the same number of negatives from each side, you're still removing balanced sets, or in this case, maybe you're thinking of adding balanced sets. You could have added 4 to each side if you wanted to, because 4 plus -4 gives you the 0, and -6 plus 4 gives you the -2. But you did have 4 negatives to take away from each side, so we could show that you were doing that. And so now you're left over with 3 x's on one side and the -2 on the other. So to get to this point, you would put into words what I just did there. She combined like terms by making 0 pairs. Then she removed 2 x's from each side, removing the balanced sets. Then she removed 4 negatives from each side to get to this point, 3x and -2. All right, so now we want to do a new problem. It says compare the expression 2 plus 2x plus -3 on mat A and 2x plus -4 plus 1 on mat B using algebra tiles. Okay, go ahead and build those yourselves using those algebra tiles in that tool. And then you have to answer the question, which mat is greater, and then use inequality symbols to show that relationship. And I showed you on the previous lesson how you could say mat A is less than mat B, or mat A is greater than mat B, or mat A is equal to mat B. Okay, so go ahead and build these and then determine what is the final answer, and then we'll do the reveal in a second. Alrighty, so our first step would be to remove the zeros, right? So you take away a couple of 0 pairs from the left, and it looks like we got 1 0 pair on the right, and that leaves you with 2 x's plus a -1, and then 2 x's plus a -3 on the right-hand side. If you remove balanced sets, we could take away 2 x's from each side, and we could technically take away a -1 from each side, but I think at this point, you know, if -1, ooh, that is not right. That is absolutely wrong. It is -1 is greater than -3 because this is more negative. 0 is greater than any negative number. So what this means is that mat A is greater than mat B, right? Whether you show it as -1 is greater than -3 or remove more balanced sets and show that nothing is greater than having negatives, all right? And if you're curious about how that is possible, just think of it this way. If you owe someone $2, wouldn't you rather owe them nothing? So 0 is greater than -2, right? It's better to owe nothing than it is to owe $2. And that's what the negative implies, is that you owe money. So 0 is greater than -2. All right. So Maria and Garth were playing a game with the algebra tiles that you see here. They grabbed a handful of tiles and put them on the expression comparison map to see who had greater value. Maria said, I have mat A, this is Maria's mat, and my side has greater value. Hooray for me. And Garth, who had mat B, naturally disagrees with her. So what we're going to start with is write down what are these two expressions. So write an expression for mat A, and then write an expression for mat B. And then you are going to work to simplify the expressions to determine which one is greater and which one is less, okay? And then explain, can you tell which side is greater, why or why not? So, So let's just start with that first. Go ahead and pause and work through that process. Okay, so this is the process you would have worked through. First, we would find the 0 pairs, and we only have one 0 pair. We have to add the 3 and the -1 here. And when we do that, we get 2x's plus 2. And on the right side, there was nothing to remove, no combining of like terms at all, so that'll stay as x plus 5. Then you may have noticed that you can take away 2 1s from each side. And you can take 1x away from each side. But you can't take away both x's. So after removing balanced sets, you're left with, in fact, let me just go ahead and show this process, right? We take away 1x from each side, and we took away 2 from each side. And what do we have left over after we've worked through that process? We have 1x on this side, and we've got the number 3 on this side. So going back to the question, what was the expression for mat A and mat B? Well, mat A was 2x plus 3 plus -1, which became 2x plus 2, and B was x plus 5. And can you tell which side is greater? Is it at all possible? And the answer is no, because we don't know the value for x. If x is like equal to 10, then Maria's right. Mat A is greater than mat B. But if x were like equal to 1, then 1 is less than 3, so that means that Garth's side would be greater, mat B would be greater. So the last part says, with your team or on your own, find at least 4 values of x that would make the expression on Matt's side greater than Garth's side. So anything that's greater than 3. So you could have said, if x is 4, then the left side is greater than the right side. If x is 10, if x is 15, if x is 1,000, anything that's greater than 3 would make mat A greater than mat B. Carl, I had a hard time keeping track of all of the solutions, which is, that makes sense, right? Who wants to list every single one of the infinite number of solutions here? She decided to try and organize her answers. First, she needed to know more about the problem. And so it says, is there a greatest number that is a solution? Is there a greatest number that would be a solution? What's the greatest possible value that you could show as a solution that makes mat A greater than mat B? And I think the answer to that is, since it goes to infinity, then no. There really isn't a greatest solution. It just keeps going on and on and on forever. And then the next question is there a smallest number that is the solution? And this is the part that gets tricky, okay? So remember, the inequality is saying that we're saying that x would be greater than 3. But where do you start? You start with the number 4? What about 3.5? That's greater than 3. What about 3.1? That's greater than 3. What about 3.0001? That's greater than 3. Is there a smaller solution for this particular situation? A smaller number than this that is still greater than 3? And you'd be right if you said yes, because we can put an infinite number of digits over here, and just as long as there's a 1 somewhere in those decimal places, then this will be greater than 3. So technically, to be able to identify a solution that is the smallest possible solution, technically you really can't. That's why when we express these solutions, we just say it's any number greater than 3. Anything that's greater than 3 will work. This works, this works, this works, this works. And of course, any number greater than 4 would work, and any number greater than 5 would work, all the way up to positive infinity. So for problem C, it says, what is special about the boundary point where the solution ends, where the solutions end? In other words, what relationship does this number have to the two expressions being compared? Well, that's kind of a confusing question. I'm just going to say that the boundary number is the value of x that makes both expressions equal, right? So if we went back to here and we showed it, if x happened to be equal to 3, then both sides would be equal, right? Because this would be 3 and that would be 3. So the boundary number that we circle there is the number that when both sides are equal to each other, x would have to be equal to that number there. So it says Carla was tired of listing so many solutions and wanted a quick way to show all the possible solutions of the inequality. So she drew this number line, and I would like for you to draw this number line too. What I'd like for you to do is circle the boundary number and then shade in the direction where all the solutions would be. Okay? Take a moment to make the number line, and then circle the boundary number and then shade the direction that you think includes all the solutions. All right, did you get the number line written in? This is how it would look. You would take your number line, and then since we're saying if x were equal to 3, both maps or both expressions would be equal, then the 3 becomes your boundary number, so you circle it. Okay, so on one side of this are all the solutions that would make map A greater. And on the other side would be all the solutions that would make map A be less than map B. Okay, so let's come back over to here for a second. If x were equal to 2, right, which is less than 3, then this side would be less and this side would be greater. That would make Garth's side better. So the boundary line separates all the numbers that are solutions from the numbers that are not solutions. And I'm going to tell you this right now. If one of these numbers on the right is a solution, then all of them are. If one of these numbers on the left is not a solution, then none of them are. So because x, in this situation, we're trying to see which one is greater, x can't be equal to 3, then we'll just circle it, not shade it in. All right, so let's go ahead and solve this inequality. It says, now consider 2x plus 5 is less than 3. Build this inequality on your expression comparison mat and record each step. Work with your team to describe the least and the greatest solutions to the inequality and draw your solution on a number line. Okay, so copy this down, work through the process, determine what your boundary number is, and then circle your boundary number and shade in the appropriate direction. All right, let's do the reveal. First off, we're going to solve this the same way we would solve an equation. We're working through the property of equality. Whatever you do to one side, do the same thing to the other, and we want to get x all by itself. So please do not be freaked out when you see an inequality symbol. The processes are the same. First thing you would do is take away 5 from each side because we want to know what 2x is technically not equal to, but we want to keep the ratios the same. So if this was an equal sign, we would want to know what 2x's were equal to before we added on the 5. Well, let's think about it the same way. Let's just remove balanced sets so you end up with 2x's is less than -2. And then if you divide each one of those in half, you end up with x is less than -1. So our boundary number that we're going to circle over here is the -1. And since x is any number less than -1, we would shade everything to the left-hand side. And since it doesn't say x is less than or equal to -1, we will not shade in the -1 itself. We'll leave that open. So the least solution, this goes all the way to -infinity. There is no least number because infinity goes on forever. But you could say this. You could say that the greatest solution is whatever the closest number that gets to -1 without actually being -1. So are you thinking that maybe -1.000001 could be a solution? Well, you can even get closer than that. So technically, I would say you can't find a greatest solution. But if you really wanted to commit to it, we could word it this way. Whatever that number was that got you closest to -1 without actually getting to -1 on this number line. So everything on this side is a solution. Nothing on this side is a solution. All right, let's copy this down and do the same thing. First, it says write a sentence in words to represent this inequality. Okay, so I'm going to read it from left to right, and you choose the words that match what I say, right? 6 is greater than 2 times x plus 2. There are a few different ways that you could express that. Go ahead and write down that in words. And then what did they get each side of the map when they simplified? Go ahead and work through the simplification process and then declare your solution and then create the graph for your solution. All right, first off, the words that you would use, obviously you got 6 is greater than on the left-hand side, but then you could say 2 more than 2 times x, or you could say 2x plus 2, or you could say 2 more than twice x. There are a few different ways you could express that expression. Now, before we answer this, we have to go through and do our legal moves. So I'm going to start by taking away 2 from each side because I want to get my 2x's by themselves. So removing balanced sets, this becomes 2x on the right side and 4 on the left. And remember, this is saying that the left side is greater than the right side. So we are trying to find all the values of x that would make this statement true. Okay, so the last step would be dividing each side by 2. So you end up with 2 is greater than x, or you can rewrite it as x is less than 2. If you rearrange the order, just remember that your inequality symbol was pointed at the x, so x has to be the lesser number and 2 has to be the greater number, right? Alligator eating the bigger lunch. So we want it still eating the 2, so x is on the left, means it's pointing still at the x, so x is less than 2. So now, how do we graph that to represent all the possible solutions? Well, 2 is our boundary number, we'll circle it, and then if x is less than 2, then x would be all of these numbers that is less than 2 on the number line. Here it says 2 is greater than x, which means that the number 2 has to be positioned on the number line in a position where it is greater than every single one of our possible values for x. So depending on how you think about it, I think this is the easier way of thinking about it. Just think x is going to be to the left, it's less than 2. Okay, so answer this question, Mat A, once everything was fully simplified, was the number 4 or the number 2, I suppose. And then Mat B would be the 2 x's or just the 1x. I decided for some reason to declare what Mat A was when we were here and what Mat B was when we were here, because we aren't really talking about doing that last step of dividing each side by the same thing. We're just simply talking about removing zeros and removing or adding balanced sets. So just give you an idea of my mindset when I created those answers. And that is it. We are done with today's lesson. So let's move on to possibly a check for understanding or for sure the homework. Take care. Bye. Bye.
Hey, feeling good.